In the previous two videos, Dr. Hossein explained how a neural network works. We learned about all the basics and essential components of neural networks, such as neurons, layers, forward propagation, back propagation, learning rate, epochs, and batches. Now that we are familiar with the neural networks, let us write code for a neural network using Python. When we discussed how neural networks work, we used a data table as an example. The table contains water, salinity, and fertilizer amounts, these three features. The target was to predict pecan yield. As a full disclosure, I am an artificial intelligence text-to-speech voiceover that Dr. Hossein is using for this video to expedite the video production. Okay, we have the real data table. Note here that we have a column named row ID, which has 1, 2, 3, and so on, a serial number just to identify in which row someone is. Pecan production does not have anything to do with the row ID column. So, we will drop this column before training a neural network using this data. These features, water per acre, salinity level, and fertilizer per acre, against which the pecan yield is provided, are the important features that will contribute to the neural network training. Okay, let's start by importing NumPy, Pandas, and Matplotlib's pyplot. I am reading the file. It is tab separated, so I am using the delimiter \t. The file name is pecan.txt, so I am correcting the file name. df is the data frame that has the data. Now, I am visualizing the relationship between water per acre and pecan production. The more the water, the more the pecan production. Makes sense. The more the salinity level, or the salt in the soil, the lesser the pecan production. That makes sense too. The more fertilizer there is, the more pecan production, as seen in the data. That is great. We just explored the data a bit so that we know what we are dealing with. Now, I am dropping the row ID column from the data frame. So, the variable data does not have the row ID column anymore. From the data variable, I am now separating the three columns in the variable x. So, x contains water, salinity, and fertilizer. I am taking the pecan yield column in variable y. Therefore, x has the input data, and y has the output. Against each row of x, there is an output in y. X is a two-dimensional NumPy array. Y is a one-dimensional NumPy array. Number of rows in X is equal to the number of elements in Y, obviously. Now I am importing the PyTorch functionalities. NN is for neural network-related functions. Optim is for optimization-related items. I am also importing scikit-learn's train_test_split that I will use to split the data into two parts, training and test, so that I can train the neural network using the training part and evaluate the model using the test part. Scikit-learn's StandardScaler will help us in bringing the features to reasonable standards. Sometimes, the ranges of the values in the columns can vary drastically, which may result in model weights that learn only prominent large-valued features. So, we will be standardizing the data. Data loader in tensor dataset will help us run iterations and create batches. Here, I am splitting the data into training and test sets with 80/20 splits. That is, 80% of the data will be in one part, which we will use to train the neural network. Another part will contain 20% of the data, which we will use to evaluate the model. In the train_test_split function, we specify the proportion of the dataset that should be allocated to the test set. Here, 0.2 for the test_size variable means 20% of the data will be used for testing, and the remaining 80% will be used for training. If you use random_state equals 42, for the pecan production data we have, your training and test set will be the same as mine. Other than that, this random_state is not necessary. X_train will have 80% of the rows of X, Y_train will have the corresponding pecan yield. X_test will have the rest 20% rows of X, and Y_test will have the corresponding pecan yields. This line creates an instance of scikit-learn's StandardScaler class. The StandardScaler is a tool that standardizes features. It transforms your data so that each feature, column, has a mean of 0 and a standard deviation of 1. Standardization is important in neural networks because it ensures that all input features contribute equally to the model's learning process. Without standardization, features with larger ranges might dominate the gradient updates, leading to a slower or unstable learning process. This line fits the StandardScaler to the training data and then transforms the training data according to the scaling parameters, mean and standard deviation, calculated during fitting. Fit_transform performs two operations, fit and transform. Fit computes the mean and standard deviation of each feature in the training data. Transform applies the scaling, standardization, to the training data based on the computed mean and standard deviation. By fitting the scaler on the training data, you ensure that the model learns the scaling parameters from the same data it will be trained on. This helps in achieving consistency during training. The transformed x_train now has features that are centered around 0 with a standard deviation of 1, which improves the efficiency and convergence of the training process. This line applies the same transformation, standardization, to the test data that was applied to the training data. However, it only uses the transform method and not fit_transform, because we do not want to refit the scaler to the test data. The transform method scales the test data based on the mean and standard deviation calculated from the training data. Why is it important that we only apply the transform function for test data using the mean and standard deviation calculated from the training data? Consistency is key when evaluating the model. By using the same scaling parameters from the training data to transform the test data, you ensure that the model's performance is evaluated on data that has been processed in the same way as the training data. This helps in accurately assessing the model's ability to generalize to new, unseen data. Also, we did not apply fit_transform to the entire training and test data because we did not want the training phase to know the global mean and standard deviation. When training a machine learning model, it's important to ensure that the model is evaluated on data it hasn't seen during training. This helps us understand how well the model generalizes to new, unseen data. The fit_transform method calculates the mean and standard deviation of the data it's applied to. If you apply fit_transform to the entire dataset, that is, training and test data together, the scaler will calculate a global mean and standard deviation that includes information from the test set. This introduces a form of data leakage because the model would effectively know some information about the test data during training, which could lead to overly optimistic performance metrics. By fitting the scaler only on the training data, we ensure that the test data remains unseen and independent, providing a true assessment of the model's performance. Okay, now we have x_train and x_test. Should we standardize y_train and y_test? It's less common to standardize y compared to standardizing input features, x, because the primary goal is often to preserve the interpretability of the output y. Most models can handle target variables that are not standardized, especially when y is already in a reasonable range or when the interpretation of the predicted values in their original scale is important. For example, the pecan production amount. When should we consider standardization of y? If y has a large range or is on a very different scale compared to the input features, standardizing y can help the model learn more effectively. If y has a highly skewed distribution, standardization or another transformation, like log transformation, might be applied to make the learning process smoother. If there are multiple outputs, that is, multiple y features, and they are on significantly different scales, standardizing each output can help the model treat each output with equal importance during training. Even in multi-output situations, standardizing y is not always necessary unless there's a specific reason related to scale, distribution, or numerical stability. If you standardize the y value, you must inverse transform the predicted value to make the prediction interpretable. We are not transforming our y values anyway. Now, let's convert data to PyTorch tensors. This line converts your training input data x_train into a PyTorch tensor. We have to use PyTorch tensor as our data structure because we will use PyTorch to construct our neural network. The torch.tensor function converts a NumPy array or any iterable into a PyTorch tensor. X_train is the input data for training, typically a NumPy array or pandas data frame. Float32 specifies that the tensor's data type should be float32. This is a common data type for numerical data in deep learning because it balances precision and memory efficiency. X_train_tensor is now a PyTorch tensor that can be fed into a PyTorch neural network for training. This line converts your training target data y_train into a PyTorch tensor and ensures it has the correct shape. Similar to the previous line, this converts y_train, the target values for training, into a PyTorch tensor with a float32 data type. View-1,1 reshapes the tensor to ensure it has two dimensions. The the first dimension is inferred from the data. -1 means PyTorch will calculate the appropriate size based on the data. The second dimension is set to 1. Note that our y_train was a one-dimensional array because it only has pecan yield. Y_train could have multiple features, such as, along with pecan yield, there could be pecan plant growth. That means, ideally it is expected that the output is also a two-dimensional array instead of a one-dimensional array. That is what this line is doing, converting the one-dimensional y_train to a two-dimensional PyTorch tensor. Y_train_tensor is a 2D PyTorch tensor with number of rows equal to however many cells you have in the y_train array and exactly one column. X_test_tensor is the respective PyTorch tensor for test input data x_test. Y_test_tensor is the test target data y_test in a PyTorch tensor and ensures it has the correct shape. So, in this part, we just converted our data into PyTorch data structures. This line creates a tensor dataset object, which is a dataset that holds both your input data, x_train_tensor, and target data, y_train_tensor, as paired samples. This dataset can then be fed into a data loader to facilitate batching, shuffling, and other operations during training. Train_dataset now contains all the training data and pecan yields, organized as pairs of input and output tensors. This dataset is now ready to be passed to a data loader for further processing during training. This line creates a data loader object from the train_dataset. The data loader object, train_loader, will handle the batching and shuffling of the data for training. The data loader is a crucial component in PyTorch for efficient data handling, especially when dealing with large datasets. It automatically handles batching, shuffling, and loading data in parallel using multiple workers. Train_dataset here is the dataset object created in the previous step, containing the paired input and target tensors. Batch size equals 16 specifies the number of samples per batch. In this case, the data loader will return batches of 16 samples at a time during each iteration. As in Dr. Hossain's previous video, we have studied that batching is important for efficient training, as it allows the model to update its parameters after processing each batch rather than the entire dataset at once. The shuffle equals true option ensures that the data is shuffled at the beginning of each epoch. Shuffling is important to prevent the model from learning patterns based on the order of the data, which could lead to overfitting. We will learn about overfitting later. Train_loader is now an iterable object that, when used in a training loop, provides batches of input and target data in shuffled order. Each batch generally contains 16 samples, as specified by batch_size equals 16. However, the last batch might contain fewer than 16 samples if the total number of rows in the training data is not an exact multiple of 16. This is because the data loader will divide the dataset into batches of 16 samples, but any remaining samples that don't fit into a full batch will still be included in a smaller batch at the end. Out of 54 rows of the original data, 44 rows are in training, which is close to 80%, and the rest 12 rows are in the test data. Now, we are going to create a neural network. This line defines a new class named neural network that inherits from nn.module, the base class for all neural network modules in PyTorch. By inheriting from nn.module, the neural network class gains access to all the tools and functionalities provided by PyTorch for creating and managing neural networks, including methods for parameter management, forward pass definition, and more. Here is the constructor. This line calls the constructor of the parent class, nn.module. It ensures that the neural network class is properly initialized, allowing it to use the methods and properties inherited from nn.module. Now, we are defining the layers here. The nn.linear function creates a fully connected, or linear, layer in the network. The first variable, fc1, refers to the connections between the input layer and the first hidden layer. In the input layer, we have 3 inputs, since the pecan production data has 3 features. In the first hidden layer, you can set the number of neurons. Here, we are setting the number of neurons to be 10. For fc2, we will encode the connections between the first hidden layer and the second hidden layer. The first hidden layer has 10 neurons, which we already mentioned in the previous line. So, we will need exactly 10 here for fc2. Okay, let us make it 4, to make sure that we have the accompanying illustration the same. So, if we have 4 neurons in fc1, then fc2 must start with 4 neurons. Then, we mention how many neurons there should be in the second hidden layer. We are mentioning that there should be 5 neurons. Now, from these 5 neurons, we want to directly connect the output layer. Remember, the output layer has only one output, pecan yield. Therefore, the output layer will have exactly one neuron. That is, FC3 is also fully connected and maps the 5 inputs from the previous layer down to a single output. Okay. We have defined the neural network architecture through FC1, FC2, and FC3. One very critical item that we need to understand is how many parameters we have in a neural network. What does it mean by the term neural network parameters? Neural network parameters are weights and biases that the forward and backward propagations will fix. The more parameters, that is, the more weights and biases we have, the more computations will be required. We can count number of weights and biases. In this neural network we have 3 inputs, 4 neurons in the first hidden layer, 5 neurons in the second hidden layer, and 1 neuron in the output layer. Each neuron has a bias, for sure. The number of neurons is 4 plus 5 plus 1 is equal to 10. Each neuron has a bias, and hence, there are 10 biases for sure. There is no bias in the input layer, because the input layer contains feature values, not any neuron. Now, let us count the number of weights. Each neuron of the first layer will handle weights for each input. That is, each neuron in the first hidden layer handles 3 weights. So, 4 neurons in the first hidden layer will handle 4 times 3 is equal to 12 weights. The second hidden layer has 5 neurons. Each neuron in the second hidden layer will handle 4 inputs, that are actually the outputs of the 4 neurons of the first hidden layer. Therefore, total weights that the second hidden layer handles is 5 times 4 is equal to 20. The output layer has 1 neuron that has 5 inputs, of course those are outputs of the 5 neurons of the previous layer. So, there are 5 weights handled by the neuron of the output layer. Total weights in the entire neural network are 12 plus 20 plus 5 is equal to 37. We already counted that there are 10 biases. Therefore, we have a total of 37 plus 10 parameters, which is equal to 47 parameters. The neural network will tune 47 parameters in total. To generalize the number of inputs, I am using the number of features of x_train. Also, we use something similar for defining the number of neurons in the output layer. Hardcoding to 3 for input nodes, and 1 for the output layer is also fine for this dataset, but in that case if you change the input data table, the layers might not work. Okay. At this point, we will define forward propagation. The forward method defines the forward pass of the network, specifying how the input data flows through the layers to produce an output. This method is automatically called when you pass data through the model. The input X is passed through the first fully connected layer, FC1. The output of this layer becomes the input to the next layer. The output from FC1 is passed through the second fully connected layer, FC2. The output from FC2 is passed through the third and final fully connected layer, FC3, which produces the model's prediction. You could add activation functions, such as ReLU, after each layer to introduce nonlinearity, which is often necessary for the model to learn complex patterns. For the dataset we are using, we do not need much complexity. Also, we want to keep it simple for better understanding. Okay, what we have done in this class. By inheriting from NN module, the neural network class gains access to PyTorch's powerful neural network building capabilities. The network consists of 3 fully connected layers, where each layer's output is passed as input to the next layer. The forward method defines how data moves through the network during the forward pass, ultimately producing the model's predictions. This simple neural network structure is common in basic regression tasks, where the goal is to predict continuous outputs based on multiple input features. So far, we have just defined the neural network. We have a little more to go in terms of training the neural network. Let us build an instance about neural network class. Model equals neural network. The model object now represents your neural network, with its layers and connections set up according to the structure defined in the neural network class. This model will be used to perform both forward and backward passes during training. It contains the parameters, that are weights and biases, that will be updated as the model learns from the data. Criterion equals nn.L1 loss. This specifies the loss function to be used during training. L1 loss, also known as mean absolute error, MAE, calculates the average absolute difference between the predicted values and the actual target values. Remember, Dr. Hossein in his earlier video was computing the absolute difference between each predicted output and the known pecan yield, and summing them up all. L1 loss does the same thing. It averages all those differences. Optim.atom creates an optimizer using the atom algorithm, which is a popular and efficient optimization algorithm that combines the advantages of two other algorithms, AdaGrad and RMSProp. Atom adjusts the learning rate for each parameter individually based on estimates of lower-order moments. We will not go deep in that discussion. Model.parameters passes the model's parameters, that are the weights and biases of the neural network, to the optimizer. These are the parameters that will be updated during training to minimize the loss. LR equals 0.01 here. The LR argument sets the learning rate for the optimizer. The learning rate controls how much the model's parameters are adjusted with respect to the loss gradient during each update. A learning rate of 0.01 is a commonly used starting point, but it may require tuning depending on the specific problem. This setup prepares your model for the training process, where it will iteratively learn from the data by minimizing the loss function using the atom optimizer. Let us write the code for the training loop now. This loop iterates over the specified number of epochs, 200 in this case. Each epoch represents a full pass through the entire training dataset. The model will train on the data 200 times, allowing it to iteratively learn and improve. The model.train function sets the model to training mode. This is essential because certain layers, like dropout and batch normalization, behave differently during training compared to evaluation. In training mode, these layers update their internal states and apply regularization, like dropout, which is crucial for preventing overfitting. For the dataset we are working on does not have that level of complexity. Still, we will always make sure that our model is in training mode during training. This line ensures that. This loop iterates over the batches of data provided by train_loader that we prepared before. Batch_x contains a mini batch of input features, and batch_y contains the corresponding target values. Batching allows the model to update its parameters more frequently and reduces memory usage, especially when working with large datasets. Before performing backpropagation, it's essential to reset the gradients of all model parameters to 0. In PyTorch, gradients accumulate by default, so if you don't zero them out, they will be added to the gradients computed in the previous iteration, leading to incorrect updates. Predictions equals model batch_x. This will call the forward function of the model. The forward pass computes the model's predictions for the current batch of input data, which is batch_x. The output is stored in the predictions variable, which will be compared against the actual target values in batch_y to compute the loss. The loss function, defined earlier as criterion, calculates the difference between the model's predictions and the actual target values, batch_y. This difference is quantified as the loss, which the model aims to minimize during training. Loss.backward. Backpropagation computes the gradients of the loss with respect to each model parameter, weights and biases. These gradients indicate how much each parameter should be adjusted to reduce the loss. The backward function computes the gradients, but it does not change the weights and biases. Optimizer.step updates the model's parameters based on the computed gradients. The parameters are adjusted to minimize the loss, which should improve the model's predictions over epochs. To keep track of the loss, let us introduce a variable total_loss here, sting it to 0. The loss.item method extracts the scalar value of the loss and adds it to total_loss. This accumulates the total loss for all batches in the current epoch. After all batches in the epoch have been processed, the average loss for the epoch is computed by dividing total_loss by the number of batches, which is the length of train_loader. The average loss is printed at the end of each epoch, allowing you to monitor the model's learning progress over time. This training loop is a fundamental part of training a neural network. It involves iterating over the dataset multiple times, processing the data in many batches, computing the loss, and adjusting the model parameters to minimize this loss. By printing the average loss after each epoch, you can track how well the model is learning and ensure that it's improving as expected. Running it, we see that the average loss is reducing over the epochs, which is really good. We could probably finish way earlier than 200 epochs. In the last 100 or so epochs, the average loss was almost similar. That means, we ran more epochs than we needed. Anyway, it does not hurt to run more epochs than required for this data. For other datasets, it might be ideal to stop as convergence is observed. Now, we have our trained model. Time to see how good the model is. Remember, we have the test data separated. The x_test_tensor variable has those test inputs that the trained model did not see during training. For those inputs, we will predict the pecan yield. We will compare the predicted pecan yields with the actual pecan yields that are stored in y_test_tensor. Let us start the testing phase by calling the model.eval function. The model.eval function sets the model to evaluation mode. This is crucial because certain layers, like dropout and batch normalization, behave differently during training and evaluation. So, common practice is that we use model.train mode for training phase and model.eval for the evaluation phase. With model.eval, the forward pass will not do the extra work of remembering many of the steps, because in evaluation mode we will not do any backpropagation. Backpropagation is for training only. We run the forward phase, keeping in mind that there is no backpropagation in the evaluation phase. The torch.no_grad context manager temporarily disables gradient computation in PyTorch. This is important during evaluation because gradients are not needed for inference or prediction. Disabling gradient computation saves memory and computational resources because, with torch.no_grad, PyTorch will not track the operations for gradient calculations. So, torch.no_grad can lead to significant performance improvements, especially when dealing with large models and large test datasets. This line performs a forward pass through the model using the test data x_test_tensor. The model generates predictions based on the latest parameters of the model. The predictions are the model's outputs for the test inputs, and these predictions will be compared to the actual target values, y_test_tensor. We now have the test_loss. We print it. Test loss will demonstrate the loss, however, a standalone loss might not give you a concrete idea about whether the prediction was great or not. Let us print the test_predictions variable. Let us also print the actual pecan yields. The predicted pecan yield is 432.4279, whereas the actual pecan yield is 430.4150. The predicted pecan yield is 502.3425, whereas the actual pecan yield is 500.00. So on. Notice that their predictions are pretty good. We can go back to the neural network, change the number of neurons, the learning rate, batch size those hyperparameters, and try to see if the test predictions can be any better. Once we are satisfied with the predictions using the test data, we can deploy the model that we have built. Let us assume that we are satisfied with the predictions for now. Now, how can we see the weights and biases of our trained model? We write this function print_weights_n_biases for inspecting the internal parameters of the neural network model in PyTorch. The function takes the model as an argument, which is an instance of a neural network, that we defined by subclassing nn.module. Model.named_parameters function returns an iterator over the model's parameters, yielding both the name of the parameter, such as fc1.weight or fc1.bias, and the parameter tensor itself. The parameters include both the weights and biases for each layer in the network. The loop iterates through each parameter in the model. For each parameter, name contains the name of the layer and the type of parameter, weight or bias, and param contains the tensor representing the actual values of that parameter. Param.requires_grad indicates whether the parameter is part of the model's trainable parameters. By checking if param.requires_grad, the function ensures that it only prints the values of parameters that are trainable, that is, those that were updated during training. Printing the names and values of the parameters. Overall, for each trainable parameter, the function prints the layer's name and the actual values of the weights or biases, which can be useful for debugging, understanding model initialization, or monitoring changes during training. We will use the function to inspect the weights and biases of the trained model we have now. We call the function with our model in variable named model. Here are the weights and biases of each fully connected layer, FC1, FC2, and FC3. That is all good. We have our model. It performs well with our test data. Now, let's say that when the model is deployed, I have a completely different dataset. Here my data contains 3 rows. These 3 rows are 3 samples. The first sample has its water per acre, salinity level, and fertilizer per acre. The second sample also has those 3 features. The third row or sample also has those three features. Now, we want to predict for these three samples. This line applies the same transformation to my data that was used on the training data. It's crucial to use the same scaler, that is the variable scaler, that was fitted during training to standardize the data. We have to standardize any new data based on our training standardizer because our neural network is familiar with standardized data, not regular data. Hence, if we want to use our model as a pre-trained model, we have to save two things, the model itself and the data standardizer we use to transform the data for training. So, the model variable and the scalar variable will need to be saved if we want to use the model later. Now, transforming the data is not enough. Our model uses PyTorch tensor, so we will have to convert the transformed new data to the PyTorch tensor data type that our neural network model is familiar with. Now my_data_tensor can be used in a forward propagation of the model to predict the pecan yields for the three samples. We use model.eval to put the model into evaluation mode. We stop unnecessary calculations with torch.no_grad. We send my_data_tensor to the model to run the forward propagation and have the predicted pecan yields. Here are the predicted pecan yields. Notice that with lesser salinity, we have a higher pecan yield. With more salinity, we have lesser pecan yields, just like we observed before using some visualization. I suggest that you test more by changing the code. Just as a curiosity, my_data_transformed has the numbers very small because there are transformed data points. The transformed data points may even have negative values even if your original data points are not negative at all. The reason is that, with standardization, the mean becomes 0. Hence, some values may be negative and some can be positive to make the feature average 0. Now you have this whole code for neural network modeling, testing, and also using the trained model for completely new data. PyTorch gives us quite some flexibility, which is amazing because you can monitor the epochs. All the neural network related codes could be written using just 3 lines of code using another package. In the description section, I will provide a link to a video that shows how to construct a simple neural network using 3 lines of code.